Hi, in this lectures, we are going to study the stress in another type of structures, the so-called thin-wall pressure vessels. As you should have seen in reality, cylindrical or spherical pressure vessels are commonly used in industry to serve as boilers or storage tanks. In order for us to design such vessel, we need to understand the stress distribution for this type of structures. It should be noted that in this course, we will limit ourselves to the analysis of vessels that have thin wall, which will be defined shortly. The reason is for such vessel, the stress can be analyzed in a rather simple manner. That said, let us discuss some terminologies related to these topics. Assume what we are looking at right now is the exterior appearance of a gas tank or vessel. Let us use an imaginary cut at this location to look at the inside. Then first, thin wall pressure vessels are defined as though having inner radius to wall thickness ratio greater than 10. Second, gauge pressures is defined to be the value above the atmospheric pressures. In other words, the gauge pressures is calculated by subtracting the atmospheric pressures from the true pressures inside the vessel. Now let us try to understand stresses in thin wall pressure vessels. Specifically, we will study the stresses for a cube element of materials in the main body of the vessel and being oriented as shown on the screen. To see it better, let us zoom in the element. Then here will be a simplified state of stress of the element with the circumferential, longitudinal, and radial stresses. Since for thin wall vessels, the radial stress sigma 3 is very much smaller than the longitudinal stress and circumferential stress, or sigma 1 and sigma 2, it is usually ignored in the analysis. That said, let us first determine sigma 1 circumferential or hoop stress. For that, we will use imaginary cuts to study the equilibrium of this portion of the vessel. For convenience in calculation, imagine we will include in the free body diagram the gas associated with the portion. For notation, let us set up a coordinate system and describe the dimension of the portion. Then to find sigma 1, we will consider the equilibrium of the portion in the x direction. In that direction, the portion is subjected to a force caused by the gauge pressure. To keep the portion in equilibrium, that force is balanced by another force resulting from the hoop stress that we are trying to determine. Put it differently, sum of the forces in the x direction has to be 0. From here, we can obtain the equation to find the hoop stress. Next, we can find together the longitudinal stress. For that, let us use this plane to cut through the vessel. Keep one half to study the equilibrium. Use the coordinate system that we had before, but this time we will study the equilibrium of forces in the y direction. That said, the first force in the equation will be the one caused by the pressures. The second force is the resultant of the longitudinal stress. Here is the equilibrium equation in the y direction. From here, we can obtain the equation to find the longitudinal stress. Next, let us study the stresses in spherical vessel. Let's say we study the stresses for this element. Then, based on symmetry, the state of stress for the element will be the following. As you can see, we no longer have different stresses in different directions. Instead, as you can see, we have a single value of stress of the same value as the longitudinal stress in cylindrical vessel. Let us prove that. Like before, to find the value of the stress, we will section through the vessel by a plane going through its center, and consider the equilibrium of 1/2. Like we did with cylindrical vessels, if we consider the equilibrium of forces in the y direction, the first force is the result of the gauge pressures, and the second force is the result of the stress we need to find. From the equilibrium equation in the y direction, we can obtain the formula to find the stress. You can see that this formula is the same as the one to find the longitudinal stress in cylindrical vessels. That's all for this lecture. Thanks and see you in the next one.